Today we're going to be talking about substitution, specifically SN1, SN2, and competition between the two. So as a reminder, SN2 reactions happen in a single step, and in terms of rates of reaction, anything that affects this step affects the rate of the reaction. SN1 reactions, on the other hand, have a slow rate-determining step in which a leaving group leaves, leaving behind a carbocation, and the nucleophile is not involved. So slow step determines the rate. And again, it's about anything that would make this leaving group leaving happen faster. There are two additional reactions that can happen with alkyl halides as substrates. One of them is our elementary step with 3 arrows, E2 elimination, in which both a base and a substrate are there at the same time. This reaction involves a leaving group leaving next to a carbon with an H. A second type of elimination reaction goes through the same rate-determining step as SN1. So this first one's called E2, and it involves only the leaving group leaving in the slow step. It shares the same rate-determining step as SN1, and in fact always competes with SN. We will look at these elimination reactions in more detail during the last week of the term. So ultimately, what we're working towards is, if we have an alkyl halide, deciding what kind of reaction it will do. This picture is out of page 210 out of your Stromanis textbook, and we will be looking at it in more detail next week. So going back to SN2, just as a review, the more crowded the substrate, or the larger the nucleophile, the harder it is to do the opposite side attack that's necessary, and very hindered substrates will undergo very, very slow SN2 reactions, so slow that something else will happen first. On the other hand, methyl has the smallest electron cloud and will react fastest. Once you make it primary, it's a little more crowded, secondary, even more crowded, and therefore methyl, primary, secondary are the relative rates of the reactions. Since the nucleophile is involved in the rate-determining step, the strength of the nucleophile can also affect the reaction rate, and in particular, neutral nucleophiles, or nucleophiles with spread out negative charge, react more slowly than negatively charged nucleophiles. And of course, since the leaving group leaves during the reaction, the faster reactions will go with better leaving groups. Iodides, tosylate, mesylates, triflates are the fastest. Weakest conjugate bases, followed by bromide, chloride, fluoride, and generally anything more basic than the fluoride ion does not leave as a leaving group at all, and that includes our negative charge on oxygen or nitrogen. And neutral water, which is groups that are protonated prior to leaving, is a similar ability to leave as tosylates and iodides. So the solvent also impacts this reaction because a solvent can impact the nucleophile. In particular, are aprotic solvents. They generally show up as letters like DMSO, DMF, acetonitrile, HMPA, or acetone. They have no or NH, aprotic, and they make the reaction faster, while your so-called protic solvents, the ones that are able to hydrogen bond, occur more slowly. And the reason for this is that your protic solvents solvate the nucleophile really well, making it effectively larger and harder to do an SN2 reaction. So as a summary, the variables for SN2 reactions are alkyl group, less hindered is faster, and allylic and benzylic of the same substitution will react a little bit faster for both electronic and steric reasons. You saw this in the lab when crotyl chloride and benzyl chloride had reactivities faster than a regular primary chloride, butyl chloride did. The leaving group, the weaker base is better. And you saw this in lab when reactions of the same substitution with a bromide leaving group was faster than chloride. For example, sec-butyl chloride to sec-butyl bromide, or butyl bromide was faster than butyl chloride. And finally, the effect of the nucleophile. If it's charged, it's going to be a stronger nucleophile than neutral. If it's got localized charge, it's stronger nucleophile than a delocalized charge. And in certain solvents, larger nucleophiles are better than smaller nucleophiles. Finally, in solvents, a protic tends to favor SN2 even more because protic solvents solvate the nucleophile and slow down the reaction. So just as an example, here are some common solvents for nucleophilic reaction. The ones on the top are all protic. They all have OHs. Anything with an OH or NH is capable of forming hydrogen bonds and will tend to slow down SN2 reactions. Solvents that are often represented by letters or words that have no or NH, even diformamide has H's and it has N's and O's, but no NH. These are aprotic solvents and they tend to favor SN2 reactions. So let's talk for a few minutes about the factors that influence SN1. So as a reminder, the slow rate determining step of an SN1 reaction is that step in which the leaving group leaves. We break a bond without making a bond. In the process, we create a carbocation, and anything that stabilizes the carbocation or the leaving group would speed up the reaction. This slide also emphasizes that once you form the carbocation, we've forgotten any chirality we had initially, and the nucleophile can approach in a later fast step from either phase to create a racemic mixture of products. The minimum number of steps in an SN1 reaction is 2, one of which is leaving group leaving to create a carbocation and a halide. This is the reaction that determines the rate. And anything that can stabilize a carbocation makes the reaction faster. Turns out that the more alkyl groups you have, the more stable the carbocation. Tertiaries more stable than secondaries, more stable than primary. It also is true that conjugation can stabilize a cation. And in fact, a primary allylic and a primary benzylic is about as stable as a regular secondary carbocation. So reactions will be on the same order of magnitude. You saw this in lab when you did the SN1 reaction, and both benzyl chloride and proto chloride reacted when primary other chlorides did not. And here we have electron density pictures that kind of emphasizes the localization or delocalization of positive charge. Localized is less stable. And on the methyl or the primary, we have a strong blue area, which is the delta positive. Secondary, you see the delta positive is less pronounced. Tertiary, there's no blue at all. And benzylic or allylic share the positive charge, so there's no strong localized positive charge, more stable. And here's a resonance picture of the same thing. In the allylic carbocation, you have 2 centers to share the plus charge equally. In benzylic, you have plus charge shared between the carbon external to the ring and the ortho, para, ortho positions. In all cases, these positions are where the leaving group has left. And here's some relative rates. Shows you that secondary isopropyl chloride, allylic chloride, and benzylic chloride will all react at about the same rate or within the same order of magnitude. Making it tertiary makes it much, much faster, similar to dibenzyl, having 2 delocalizing groups. And if you put 3 delocalizing groups, triphenyl next to the leaving group, you go even faster. So a typical kind of problem, and this might be a smart work, put things in buckets, is to rank the compounds in terms of increasing SN1 reactivity. To do that, you want to define what kind of carbon is attached to the leaving group. And in the first one, the carbon attached to bromine has only 1 bond to carbon, primary. In the second one, we have 2 bonds to carbon on that carbon with leaving group, secondary, but it's also next to a pi bond, allylic. The third one is kind of odd in that the halide is attached directly to an sp2 center. This reaction will occur much more slowly, and in fact, impossibly slow, so something else will always occur, no matter what the reaction conditions. If it's not an sp3 carbon, it won't do SN2 or SN1. We saw this in the lab when we looked at bromobenzene, which was an SN2 center next to a bromine, and we should not have gotten reaction in either the SN1 or the SN2 reactions. And then D is just a plain old secondary. The carbon attached to the leaving group has got 2 other bonds to carbon. So in terms of rates, C will never react. It's so slow. A is primary. It will probably won't react because something else will happen faster. D is an ordinary secondary. It will react a little bit more quickly. And B is a secondary allylic. It will react fastest of all. So fastest to slowest. Because a leaving group leaves during the rate determining step for SN1, the effects on rates are the same for SN1 as they are for SN2. That is, better leaving group is faster reaction, with water, tosylate, mesylate, triflate, and iodide all being the best leaving groups, and slightly stronger bases, bromide or chloride, are worse leaving groups, and you'll never see a negative charge on oxygen or nitrogen as a leaving group. Finally, for solvent effects for SN1, we would find that the more polar, the better. And the more polar because the leaving group is stabilized by polar solvent and the carbocation intermediate is stabilized by a polar solvent. And both those impacts will lower the activation energy to create the carbocation and the leaving group. Here's an example of how the more polar solvent increases the rate. In all these reactions, we have exactly the same substrate, nucleophile, and the rate determining step being tertiary SN1 is this leaving group leaving. And with ethanol, which has some carbons with its less polar versus water, more polar, the reaction is much faster in water than ethanol. And in fact, the more water you put into an ethanol water mixture, the faster the reaction. So as a summary, the variables for SN1 rates are any alkyl group that makes a carbocation form more stable will increase the rate of the reaction, with tertiary being much faster than secondary and so much faster than methyl primary you won't see them. And having conjugation with allylic or benzylic systems, pi bonds next door, makes the reaction faster. A leaving group effect is the same as it is for SN2, with a weaker base as a better leaving group. The nucleophile is not involved in the rate determining step. Very strong nucleophiles or bases will tend to favor other reactions like SN2 or E2, but it will not impact the rate of SN1. And solvent, the more polar, the better. And many times you'll see the protic solvents are the most polar. So here's a contrast. SN2, of course, is bimolecular, everything happening at once, both the nucleophile and the substrate in the rate determining step. SN1, only the substrate is in the rate determining step. SN2, there's at least one step, and there might be acid-base reactions as well. SN2, there's at least SN2 has one step. SN1 has two steps, plus any acid-base reactions. The substrate effect is exactly opposite for substitution between SN2 and SN1, with methyl primary reacting exclusively by SN2, tertiaries reacting exclusively by SN1, and secondaries reacting by either one depending on reaction conditions. And then allylic and benzylic slightly accelerates SN2 reaction, but greatly accelerates SN1 reaction rates. Leaving group effect is the same. Weaker base is better leaving group. Nucleophile effect is only important for the SN2 because the SN1 does not have a nucleophile in its rate determining step. And for solvent, aprotic solvents favor SN2 over protic, and for SN1, it's simply polar is faster. We will have to consider that SN2 reactions and E2 reactions compete, and SN2 and E2 strengths will be considered next week. So one way to look at this problem is that if you have methyl primary, because of the unstable carbocations, you're going to get SN2 exclusively. If you have tertiary, because of the crowding, you're going to get SN1 exclusively. But if you have secondary or primary allylic or benzylic, you've got a competition going on between SN1 and SN2. It's also worth mentioning that if you have your leaving group directly attached to an sp2 center, you won't get reaction at all. So a typical kind of question might be, which reaction mechanism is active in the two reactions shown? In the top reaction, we have a secondary. Can't immediately decide if it's primary, secondary, tertiary. It is also benzylic. which tends to favor SN1 over SN1 over SN2. Our solvent, which is protic, tends to favor SN1. And our nucleophile that is delocalized tends to favor SN1. And so overall, the votes for SN1 win. This reaction will occur through a carbocation intermediate, which is resonance stabilized by the benzene ring. The bottom one is a primary, which is far removed from the benzene ring. It's got sp3 centers in between the leaving group and the benzene rings, so it's a normal primary. Unhindered SN2 is favored. We even have an aprotic solvent that will make that even faster, and so SN2 is the one. So you might be wondering why it is that the more alkyl groups attach to a carbocation, the more stable. Well, here's a figure that shows this. In particular, your p orbital, which is here on the carbocation, is empty. And anything that helps donate electron density to it helps it stabilize it or spread its electron density out. Turns out if you have a sigma bond next door, it's got a big bond to make the bond itself and a small backlobe bond. And these two lobes can help contribute electron density to stabilize the positive charge. Here we have a primary, which is only partially stabilized by the adjacent bonds because the hydrogens next door can't do this. But if you had a secondary or tertiary, you'd have 2 or 3 stabilizing reactions, making it much more stable carbocation. This is also the reason why the carbocation shifts we saw in the elementary steps tend to occur only when you can move a less substituted to a more substituted carbocation. And again, hydride shifts only occur if you can move one hydrogen or methyl group over and create a more stable carbocation. In this case, a primary being converted to a tertiary. This one will also undergo a carbocation shift with a secondary cation becoming a tertiary carbocation. And this one will undergo a hydride shift with a secondary becoming a tertiary carbocation from the 3 bonds left behind. So, to finish this assignment, you need to complete the quiz on Canvas. I'm going to do the first 2 of these 6 reactions for you, and the other 4 are going to be on the quiz. And this question asks whether this particular reaction is going to travel through SN2 or SN1. In the first case, we have a tertiary carbocation. That pretty much says SN1, and the fact that we have a very polar protic solvent and a weaker nucleophile continues to reinforce that SN1 mechanism. And the second one, we have a regular old secondary carbocation. This is where we could have SN1 or SN2 depending on reaction conditions. So we look at the solvent, it's aprotic, and that tends to vote for SN2. We also look at the nucleophile, negatively charged. Stronger nucleophile tends to vote for SN2. So this one overall would occur primarily through an SN2 reaction. Again, the Canvas quiz will let you guess the others. Another kind of problem you encounter is to see 2 reactions and say which one occurs faster. To do this, you must first decide whether it goes through an SN1 or SN2 substitution mechanism. So the reaction on the left is a primary alkyl halide. The reaction on the right is an identical primary alkyl halide. You know that the reaction is going to be SN2 because you do not create a stable carbocation. So then we look at the reaction conditions. They're both in DMF, an aprotic solvent, equal effect on SN2 rates, but one of them has a localized nucleophile, and one of them has a delocalized nucleophile with the negative charge shared between the 2 oxygen atoms. This is the stronger nucleophile, and therefore this one will go faster because the nucleophile is involved in the rate determining step. So the answer for F is that the first reaction is faster.